Hello everybody, I'm Kurt Poulsen, Oscar Zulu 7 Oscar Uniform. I will bring you to the DARC Hamradio exhibition in Frederikshavn 2012. I had the pleasure for the first time to meet Jan and Tom in person. Let's enjoy how busy these two gentlemen was Saturday morning.
After 1 year, what you can do is basically you can do the same measurement and check whether your hardware is still working okay.
Do it again. Yeah. Yes.
Hello, welcome to the Hamradio 2012 VNWA presentation by Tom Beyer. My name is Jan Verduin of SDR-Kits and I trust you will find this presentation by Tom on VNWA development, new features and some novel applications interesting. Before Tom's presentation, here is a brief video impression of the SDR-Kit stand at Hamradio 2012. Thanks to all of you who visited our stand at the fair and shared your experiences about the VNWA with us. It was great to meet you all. I'd like to thank Tom for making the presentation, but also thank Kurt Poulsen, OZ7OU, for his time and effort in producing an English version of the VNWA presentation in German, which he previously posted on YouTube. Enjoy!
When during the translation the word I is used, then it is Tom which addresses himself. First action was to find a bigger meeting room, as Tom has ordered a room for 50 people, but the one provided was not big enough, so a new one has to be found. And I think we were actually more than 50 people during the presentation. Hamradio 2012 Evaluation of the Dg8Saq Vector Network Analyzer, New Possibilities of the VNWA3. Well, let us get started. Let me first welcome all of you to my presentation of VNWA3, and I'm surprised to see how many people has shown up. Totally unexpected, but of course nice to see. Some of you know me, others do not. My name is Tom Beyer, and I am employed at the University of Applied Sciences in Ulm, teaching mathematics and physics. I am also a radio amateur since the age of 18. Previously I had professional employments working in the field of high-frequency technology at Siemens, later at EPCOS. Let me introduce the agenda for the presentation. First, what are S-parameters and how are they used? Next, how does the VNWA work and how was it created? And finally, what new features are available, with some examples shown. Regarding S-parameters, we are dealing with waves. Here we see an electronic device with input and output, which behavior can be compared to a lens, where on the left side a light beam enters, where a part is being reflected and another part absorbed in the lens, and a third part transmitted from the lens on the right hand side. All waves going toward the lens are denoted A, and all waves going away from the lens are called B. The left side is assigned number 1, input, and the right side, output, is assigned number 2. Similar behavior is seen for the electronic device under test, or called DUT, here seen inserted in the cable section. Here is a typical test object, in this case a crystal filter, symbolized by a square, where we have the incoming waves with A1 on the left side and A2 on the right side, the outgoing waves with B1 on the left and B2 on the right side. The S parameters are the ratio between B and A waves. 4 different ratios can be formulated where S1 is B1 divided by A1, S21 is B2 divided by A1, S22 is B2 divided by A2, S12 is B1 divided by A2. The test object is in this way fully defined by these 4 S parameters containing both amplitude and phase information. This picture shows the S11 equal to B1 divided by A1 of a test object, where we have the incoming wave A1 and reflected wave B1. The absolute value of S11 is the return loss and be expressed in decibel, which might look like the blue trace on the picture. The S11 can also be expressed as VSWR, voltage standing wave ratio, based on the same data but just rescaled according to shown formula. S21 is the transfer function B2 divided by A1, and on the picture can be seen that the passband transfer loss or attenuation is small, and outside the passband the attenuation is large. Our VNWA, and for that matter any other VNA, can measure these S parameters. S11 is measured based on an outgoing wave A1 delivered from TCXO to the test object, and its reflection B1 measured. The portion of the outgoing wave not reflected but transmitted through the test object is measured by the receiver RXin to yield S21. This is not a complicated situation as such to be understood. How does the VNWA function? It consists of 3 basic building blocks. First of all, we have the tunable wave generator as the source. Then secondly, 3 receivers capable of magnitude and phase measurements, which measures the incoming wave, the reflected wave and the transmitted wave. Thirdly, a control and display system is required, which takes control of all the VNWA hardware, computes measurement results and displays them. I have implemented the tunable signal generator by using a DDS direct digital synthesizer. The 3 receivers consist of 3 Gilbert cells. Note the mixer injection signals is also generated by a DDS signal generator. The IF section consists of the sound card in a PC. Control functions, data processing and display are also taken care of by the PC. A block schematic shows the reflection measuring bridge, which measures the forward wave measured by M2 and the reflected wave measured by M1. The transmitted signal delivered to RXin is measured by M3. On the top of the schematic is seen a switch which is needed to multiplex 2 of the 3 signals to the PC sound card, as a standard sound card only has 2 channels stereo. Thus, with this concept, we can measure either S11 or S21, but not both simultaneously. The first problem I had to solve was that the unfiltered DDS spectrum contained a large number of Alias frequencies, which all mix to the same IF frequency as the wanted signal at F-out, symbolized by the frequency distance between red and black vertical lines equal to the IF of 1.2 kHz, and as shown on the slide. A common solution is to suppress all signals above the Nyquist limit with a low-pass filter, limiting the usable frequency range to less than half the clock frequency. An alternative way to solve this problem is to let the RF DDS and local oscillator DDS run with different clock frequencies. By doing so, the different alliance frequencies no longer mix to the same IF frequency, but to different frequencies, symbolized on the picture by varying frequencies distance between the red and black vertical lines, and thus the frequency range can be widely expanded beyond the Nyquist limit. The VNWA1, to be shown, was the platform for these experiments. Such a VNWA1 design is practical for experiments, and I demonstrated it to my friends and colleagues at the university. My friend Professor Schumacher was of the opinion that such a device was ideal as a student project, but continuous coverage to the UHF frequency range was a must, and it should be reproducible, meaning possible to build more than one unit. On the next slide, the design criteria are shown. Frequency range continues to beyond 500 MHz, reproducible production and on a printed circuit board, lowest possible cost. Now some words about the gaps in the spectrum. A DDS is producing zero output power at the clock frequency and its harmonics, no matter which frequency it is programmed to. The solution to this problem is simply to use a variable clock frequency by such an amount that an optimum output from both DDSs is obtained on the required measuring frequency. The result of these considerations was the VNWA2 as shown here. It was controlled via the parallel printer interface of a PC, while the DB9 connector seen at the top of the PCB, and signal processing performed by an external sound card. With continuous frequency coverage from 1 kHz to 1.3 GHz, the dynamic range of more than 90 dB to 500 MHz and 60 dB above 500 MHz. Both measurements of S11 and S21 can be made. This is the basic concept of the VNWA and basically has remained unchanged up to now. In 2009, an important milestone was reached, as Dg8Saq Vnwa from SDR-Kits was bringing the VNWA to the marketplace. We quickly realized that the parallel interface of PCs was slowly being phased out, and the stereo line input, in particular on laptop PCs, was changed to a mono input. We had to find a solution, and that led to the USB interface, which can be connected to the PC by just using a single USB cable. That includes also the power supply of the VNWA. A USB sound chip is integrated on the PCB, and use of the PC sound card is no longer required. The next logical step was to integrate all of it on one PCB. The updated result is seen here, being the VNWA3 with everything on one PCB. The USB connector is seen here, the TX and RX connector is seen lower left and right, then seen the two DDS chips, followed by the two operational control chips. A further improvement of the VNWA3 is the introduction of a 12 MHz TCXO to improve the frequency stability, and the introduction of a clock pre-multiplier. Top right is seen the TCXO, and in the center the 12 MHz clock pre-multiplier with multiplication factor ranging from 2 to 8, before the clock is transferred to the DDS chips. The clock pre-multiplier also gives the possibility to better suppress noise and spike signals. This slide shows a comparison where the VNWA2 spikes seen on the blue trace, and for the VNWA3 the noise spikes are considerably reduced due to implementation of a more complex clock pre-multiplier switching scheme. Furthermore, there is the version VNWA3E available now, where E stands for expansion. It contains an optional printed circuit board with an additional USB audio codec, which allows simultaneously measurement of S11 and S21, thus reducing the measuring time by 50%. Top right is an RJ12 connector for outside world connections, where you, as an example, can connect a transfer relay or a homemade test set for automatic measurements of all 4 S parameters of a 2-port device, such that it is not needed to mechanically turn the device under test for reverse measurements. It is also possible to connect an external reference signal for improved accuracy. More on this later. Let's look at application examples. One of the major applications for the VNWA is measurements of impedances. The pictures show a typical plot for impedance measurements. The best possible way to measure impedances will be addressed in the next slides. The most common way is to connect the unknown impedance to the TX port. Then measure S11 and calculate the impedance from it. The internal bridge is optimized for 50 ohm. When loaded with 50 ohm, the bridge signal is 0. That means with impedances close to 50 ohm, the bridge is very sensitive. But by measurements of 1 kilo ohm or 1 ohm, the accuracy is a lot poorer. A second method is to measure the current flowing through the unknown impedance using the RX port. The TX port is used as a voltage source. When the unknown impedance is high, then the current is primarily depending on the unknown impedance and the measurement is sensitive. Whereas when the impedance is much lower than the output impedance of the TX port, then the current is not changing very much. This method is very good for high impedance measurements, for example measurements of small capacitances, but for low impedance the accuracy is poor. One benefit for this method is it is only required to do an S21 through calibration, but a drawback: the unknown impedance must not be grounded. A third method is to measure voltage drop across the unknown impedance, where the RX port is measuring voltage and the TX port is used as current source, although not ideal. This setup works perfect for low impedances close to short circuit, but for very high impedances the voltage does not change very much. The fourth method is to combine the two previous methods by measuring RF-IV, meaning RF current and RF voltage independently, followed by calculations of the quotients. Measurements of all impedances can be performed, both high and low impedances. Automatic measurements can be done by using an RF-IV test set obtained as a fair price kit from Ivan Makarov in Canada, which can be controlled by the VNWA software, such that I and V sweeps are made independently. To summarize, I have taken three resistors, 0.1 ohm, 51 ohm and 100 kilo ohm, and increased their values by 10% to see the impact on the measurement results, depending on the various measuring methods. By S11, reflection at 50 ohm, an enormous influence exists, otherwise hardly noticeable. For I measurements quite well at high impedances, and for V measurements quite well at low impedances, and for IV equal sensitivity for all impedances. An important role for accurate impedance measurements is of course the calibration. On this slide I will show an influence not so widely known. Here I have measured an SMD capacitor of 100 picofarad over a frequency span 10 to 60 MHz with a resolution of 0.1 picofarad. The upper blue and red trace shows the series resistance, which constitutes the loss of the capacitor, and the only trace difference is that the model for the load standard for the red trace is defined to be ideal 50 ohm, while for the blue trace a series inductance of 2 nanohenry is added. 2 nanohenry is a very small amount, less than 1% of the load value. Despite this, the error is 50% on the series resistance, while for the capacitance value hardly any influence is seen. The slightest change in the calibration load model has a great impact on the series resistance and thus the measured capacitor Q. As the imaginary part of the load standard in general is hard to determine and often unknown, it is very essential to have a quality load standard to compare with for its determination. The rescue is a new calibration method, invented by Hewlett-Packard long ago, but new to me. It is possible to repair this model error by introducing a new additional calibration standard, for example, a capacitor. The only condition is that the equivalent series resistance ESR of the capacitor standard must be known. If the ESR is 0, then the method works best possible, as no error can occur. so the Q of the capacitor used must be very high. With the false model for the load calibration standard, the blue and red trace still match, demonstrating that this error has been repaired using this new calibration method, which has just been implemented in the new 36.8 test version of the VNWA and will be included in the next general software release. Now something completely different. If you have a clock, then you always know what time it is. If you have two clocks, then you are never quite sure. I have two Rubidium standards, and I was interested to see how well they were running in sync. The idea was the following. The VNWA3E has an external clock input, and one of the Rubidium standard is connected to the external clock input. Any signal test oscillator can be connected to the RX port and then measure the phase change of the test signal relative to the reference signal and subsequently calculate the frequency difference to the nominal frequency. On this slide I have investigated how accurate frequencies can be measured by measuring the phase during 1 second of the internal TCXO against itself. As the frequency difference shall be 0, it is the VNWA accuracy we measure, and by 3 repeated measurements I got a VNWA measurement accuracy of about plus minus 10 microhertz. To measure a frequency during 1 second to within 10 microhertz with conventional frequency counters is a very difficult task. Here you see the measurement of the frequency difference between my two Rubidium standards. The red trace is the phase difference as function of time. The slope of the line, being straight, is representing the frequency difference. The green trace is the calculated frequency difference. The noise is due to numerical calculation of the derivative and other noise contributions. It is possible to directly read the frequency difference provided the frequency span is 0. We are thus measuring at the same frequency while the time increases from left to right, and as the phase difference is not 0 but drifting, the frequency difference is calculated to minus 2.5 millihertz, and the frequency variation is about 300 MHz, as even a Rubidium oscillator is not fully stable. The experts display oscillator stability with such an Allan Deviation curve, which I found on the homepage of NIST, the American National Institute of Standard and Technology, and as shown on the slide. Here you see a quite dramatic plot. I have measured the internal VNWA3 TCXO against the Rubidium standard. The green trace shows the frequency difference, and it looks quite dramatic, doesn't it? Just pay attention to the frequency resolution being set to 0.25 Hz per division. In total the frequency offset is minus 3 Hz, equivalent to minus 0.3 ppm. The specification of the TCXO is 2 ppm, so it's okay. We have now seen we can measure frequencies quite accurately. Someone in the audience suggested to display start and stop time instead of start and stop frequency for zero span. I have implemented this now, as this was a good idea. A further application for the VNWA is time domain measurements. On the slide we see a series connection of 3 coaxial cables with characteristic impedances of 75 ohm, 50 ohm and 25 ohm respectively, the latter being open. The blue trace shows the reflection characteristics in the frequency domain, which is not very informative. However, we can convert the frequency domain measurements into the time domain, as shown for the green trace, and we can now measure quite accurately the length of the cable. That means where the reflection takes place at point 1, 2 and 3, and also we can measure the characteristic impedance as 72 ohm for the first, 49 ohm for the second, and 26 ohm for the third cable. My friend PA4TIM has made an interesting measurement of a defective Christmas tree light chain to find the defective light bulb.
Christbaumkatze. Jetzt hat er Lichterkette gefunden. Das hat anscheinend tatsächlich funktioniert.
The next example shows measurements of a biscuit can acting as a cavity, and the engineering students can quickly calculate the resonance frequency. By entering the data in the shown formula for the lowest mode, the resonance frequency is 1209 MHz. When the resonance frequency measured with the VNWA, it is seen to be 1210 MHz. What happens if we fill the biscuit can with stuff? If we add material inside the biscuit can, the epsilon value increases, no more being air alone, and the frequency is lowered, quite nicely seen for the red trace. What can this be used for? Yes, indeed, it can be used as level indicator of how much stuff is inside. There are people who are interested in such a level indication, and one organization is NASA. Imagine a rocket in free space with no gravity present. The liquid fuel inside the tank is floating around, so a traditional floating level meter cannot be used, a so-called swimmer. The only way to determine the remaining level of fuel is by measuring the cavity resonance frequency of the tank. And this is exactly what the gentlemen at NASA have done. Here we see an original rocket tank spectrum measured with the VNWA3. This is not a joke. The VNWA3 is intended to fly with the rocket for evaluation. We are close to the end of the presentation, and to summarize it can be said the VNWA3 and VNWA3E are versatile test instruments which have a professional potential and are thus also being used in industry and education. For an example, we have many customers who use the VNWA for tuning pickups of NMR tomographs. Meanwhile, VNWA3 is in use on all 5 continents. I want to address special thanks to all those being supportive. Some might be missing. A final warning: VNWA makes you addicted. Thank you very much for your attention.